So, hello everyone. My name is Dr. Benjamin Sheff, and I'm here to talk to you about a recent paper that introduced Agent S. Agent S is designed to be an open agentic framework that is supposed to try and use a computer like a human would. Just interface directly with the GUI and take actions, just sort of moving around and clicking on things in the way that computers are designed to be interacted with. So the overall goal is to build this generic agentic framework, and agentic frameworks have become particularly exciting lately as LLMs have taken off. An agentic framework is taking a series of LLMs and hard-coded actions and making software combining these, capable of performing complex tasks with generic user-prompted goals. This is particularly exciting because recently there have been advances in multimodal large language models that make it possible to incorporate not just a text query, which has been big lately, but additional information in visual or even sometimes auditory prompts. It is particularly relevant in this case because what is interacting with a computer but taking in images and a goal and making a decision on action to do with that image. So interacting with the computer is a relatively straightforward application in some ways for this technology. So what does this paper seek to solve? What is there that we can't just sort of automatically do? LLMs tend to struggle with handling both long-term planning and short-term decision-making simultaneously. It tends to be difficult to have up-to-date information on how to interact with a variety of ever-changing applications that a user might want to use. And as a GUI-based agent, it has to handle a diverse set of possible interface structures and be able to quickly figure out exactly how to interface with a particular GUI and what the correct buttons are. So how do we address this, or how does Agent S address this rather? For the first issue, for long-term planning, we split up the agent into modules that are dedicated respectively to long-term planning and to short-term planning. And we set up separate databases that each of these subtasks is supposed to learn from of previous narratives for long-term planning or just previous subtasks for the short-term thing. And we'll get more into detail on that later. After each subtask, it also evaluates progress and saves summaries as a memory for future attempts, which helps handle the diverse possible structures and applications that one might have to interface with. And to help with complicated GUI structures, they do additional grounding, looking through the image, parsing out text, and marking potential interactable elements. So the overall structure on first glance looks rather complicated, but it runs from the manager, which does the sort of long-term planning, which builds subtasks that go to workers. These workers do actions. Once the workers are done with the actions that complete the subtasks, it goes back to the manager, and you keep sort of cycling through that loop until the agent in some way decides that it is done. So let's start with that planning step. The planning step takes in a user task and interprets this into subtasks that we can assign to workers. So in order to do this, we start by forming an observation-aware query. So we take in our observations and our query, and we send in this as a request for previous context. We have a separate LLM that we can ask, how do we do X? How do we do a thing? And with that, we can query through narrative memory, which is just any previous thing that Agent S has done. It saves the story and whether or not that story succeeded or failed. And it also has some amount of using Perplexica to search the web for related knowledge of how to do tasks. It combines these into a prompt edition, which is sent to the subtask planner along with our observations and user tasks in some fashion. And this generates our subtasks. The subtasks are then each handed to a worker in sequence. And a worker just cycles through actions on the observed state until a task is considered done. Um, these action decisions are enhanced by searching through previous actions, which is this episodic memory. And we can sort of look at an embedding of the current query, subtask, and context, and look for any similarity to any previous subtask that was handled, and look for what sorts of actions succeeded or failed to achieve the subtask. There's also a secondary LLM that we include that they include in the worker to keep track of the slightly bigger picture. Since the action generator is just focused on what is the current exact action that we need to do, the trajectory reflector takes a look at the current observations and asks the question, did that action actually get us closer to the goal? And is there anything I can tell the action generator to help assist it in coming up with the next action in a way that will bring us more efficiently and closer to the to achieving this subtask. Each time the subtask is completed, it runs an evaluator LLM. This evaluator makes a summary of the subtask that was how it was executed, how well that went, what the end result was, and saves that to episodic memory. If that was the last subtask, it does a very similar thing in generating a summary of how all the subtasks went and saves that as a narrative for future managers. And looking back at the context, you can see this builds our loop of manager to workers to the workers reevaluate. And when all the subtasks are done, we go back to the manager. So that's not the entirety of the thing because this grounding step is actually quite important on this side, the agent computer interface block. This is because LLMs tend to struggle with there are a couple of aspects that LLMs tend to struggle with on sort of taking a generic picture of a desktop and coming up with actions. Most notably there's coordinates. As a human, when I interact with a screen, I just sort of move the mouse and use a constant feedback loop of judging where the mouse is and where the goal is and find out where I'm supposed to click. But that is extremely processor intensive under current technologies. So really, we just need to find exactly where we're going and move instantly there. So the way that we do this is we have a couple of modules that actually try and extract what are interesting locations on the screen and how can we connect interesting locations on screen to things that the LLM might see. So this is where ID grounding, where you can mark particular IDs to particular screen elements, and OCR augmentation, where you actually feed text back into the LLM, which not only helps give it context about like locations where text is, but importantly also can give it some context about what the text is, since while multimodal LLMs are pretty good at reading text, it's still difficult to read, like on this screen, there's a lot of text. And on one shot, just looking at this and reading all of that is actually quite non-trivial. One other thing that they do to improve to improve the actions is limit the action space rather than sort of leave it open to any action that an LLM could conceive of, which consists of basically any action that any human has said online ever. We limit the actions to a few basic ones. Constrain the space so that it can try to do the best it can with tools that we know how to build. In particular, they narrow the space to a pretty good basis, to a pretty generic basis of things one might do with a computer. So you start with like click and type are arguably the most basic things that one immediately thinks of. When you want to interact with a computer, you might click somewhere or you might click somewhere and type something. Scrolling is then still an independent task. You might have to scroll around a page. Hotkeys can cover things you wouldn't be able to do just by clicks and may be more efficient at some tasks. And then you start getting into like click and drag or holds and just click and hold tasks, switching between different applications that are active, and just waiting because sometimes you run a task and the computer won't be instantly done with it. Uh, then there are a few sort of meta tasks, saving to buffer so that the LLM can remember a little bit of what's going on. If there were, say, some text, and then you have to aggregate this text with something farther down on a page, so you can save to buffer and scroll, and then telling when it's done or when it's actually failed a task. So that makes our full agent. Agent S has this full loop, managers, builds tasks for workers, workers interact with this grounded set of observations, loop a bunch of actions until it thinks it's done, the evaluator checks, and that updates a memory so that future queries and future actions are more well informed, which can even happen which may even happen on the scale of like giving a task and the episodic memory updates and it gets better at interacting with your computer. It could, in theory, get better at interacting with your computer relatively quickly. So they tested this with the primarily with the OS World dataset. This is a data set of, I believe, roughly 360 examples of tasks that someone might want to do on their computer. And these are actually fairly in-depth tasks. Like one of the examples that they had from the paper was update the bookkeeping sheet with my recent transactions over the past few days in the provided folder. And from that, it's supposed to figure out, to look through these receipts, save data from every receipt, open up an Excel spreadsheet, click through it and enter all the data that it just read. And that is an extremely non-trivial task once you start thinking about all of the individual steps that you need to do to achieve that. Non-trivial to the point that if I recall the OS World sort of default run, which I think is just sort of running GPT-4v without much other sophistication to the agent, gets something like 10% of tasks done accurately. They also ran under the Windows Agent Arena dataset, which seemed to be fairly similar, but there wasn't a whole lot of detail in the paper on how it did on that. So we move on. On OS World, we can see that depending on which actual LLM you used as the underlying decision maker for each sort of level of this agent, you got somewhat different results. Most notably, GPT-4o and Claude 3.5 seem to do the best at most tasks, and the overall accuracy at the end was sorry. Sorry, what I just said was misleading. This is sort of comparing the raw use of these of the straight multimodal LLMs to Agent S with these two different types. And we can see that the overall accuracy across different tasks is actually a substantial bump between Agent S and just using the OS World default. Especially when you start looking at daily tasks and OS tasks, that it does quite well. Even if workflow and Office, it seems to struggle with. Then they look at how much of an impact each component has. So with this little ablation study, what happens if you remove web knowledge or narrative memory or episodic memory? And it turns out that all of these aspects seem to make a significant difference. In fact, in fact, you find there's a sort of synergy between web knowledge and narrative memory, since those are both sort of different memory banks that the manager calls on, and you have a significant increase in efficiency with each independently. And you may notice the percentages don't quite match up with the last slide, but that's because this is run on a small test, a small subset that they use for testing due to time constraints. So there are a few sources for error. They sort of split possible errors into three categories. So planning errors are purely when the manager just makes bad decisions on what the subtask should be. Um, Grounding errors can be limitations from current grounding techniques. One of the examples they talk about is buttons that aren't just a uniform click anywhere on this rectangle. Since the current method of grounding is it sees an interactable element and clicks in the middle of it. And then a sort of more broadly defined execution error. So these are issues that come up during subtask execution, um, like the subtask diverging from the goal, combining multiple actions in a way that is not well defined, or occasionally just getting stuck in repeating actions, which as a member of the web agent project team, we can confirm is like a common issue that these agentic frameworks can have. Um, so there are a few directions to take future work. There's obviously working on sort of improving accuracy and using better LLMs, but in ways for things that you actually can improve just in the agentic framework, you can sort of try to fine tune the models before entering them in, or even just expanding the action bounds, things that give you a little more flexibility and could improve accuracy. But one of the other things that they talk about is that the current goals are all about accuracy. This was their target to like get a good score on the OS World benchmark, but none of these talk about speed. And it's even an acknowledgement in the ablation study earlier that they had to use this smaller subset of OS World just because this agent uses quite a lot of LLMs to do anything at all. Before the first action is called, there are at least 4 calls to LLMs. Um, and because multimodal LLMs are just a new technology that are still quite slow, the current framework can take a significant amount of time. So that's That's all I have for you. If you want to read up more in more detail on the paper, I have it linked here, or you can look, I believe there's an archive number at the head. But thank you for listening. That's my talk.